All right, guys, welcome back. This is going to be a video over 8.2, and really 8.2 is going to be broken into two parts. Folks, this is a massive section, both in importance and in sheer amount of content. It's going to be a lot of work, and I'll warn you now, it's going to be pretty difficult, okay? The definitions are pretty confusing. They're lengthy. They've got a lot of words. We use a lot of similar words. It can become confusing quick. So make sure you are taking advantage of the fact that this is pre-recorded. Pause the video. Email me questions. Make stars in your notes of what's confusing. Now, part of it you will just have to persevere through. We will at the end. I think it'll make more sense than at the beginning. But again, it's going to be tough, but you can do it. Just take advantage of pausing the video and emailing me questions, letting me know how I can help. Okay, so here's where we need to start. These are probably terms you already know, but I want to make sure you have a solid grasp on the terms and their matching symbols. Population mean is the symbol mu. It's a different looking M. It's the Greek letter mu, and it will always stand for population mean. Sample standard deviation is going to be a lowercase s. Okay, lowercase s, sample standard deviation. Sample variance is going to be the little s squared. And this should make sense because as we discussed in previous chapters, specifically chapter 3, sample or variance is standard deviation squared. So if sample standard deviation is s, sample variance is s squared. Population variance is going to be sigma squared. Again, this should make sense because we know population standard deviation is sigma. It's that O with the tail, it's the Greek letter sigma. And finally, sample mean is x bar. Okay? Anytime you see x bar, it's sample mean. And the ones we will predominantly be using are sigma, x bar, and mu. These will be the favorites, the ones that we will most likely be using. Okay? Again, you gotta know these symbols. If you need to pause the video, write these down, make note of it. If you get confused later in the video and you need to go back and reference this, please make sure you know what the symbols are, and if you're struggling with it, let me know. Okay, so here is where we're going to start. And you might be going, oh my gosh, that's so much. Okay, let me write down the first part, and I want you to write to the arrow. Then let me explain, then we'll keep going. So let me fill in some symbols here. You can pause the video and write down the whole definition, and then you can unpause it to listen to my explanation. Okay, so write down the first part to that black little arrow, including the symbols. Pause it, and then once you're done writing, listen to the explanation. So in 8.2, we are going to have two massive theorems. And what these theorems allow us to do is they allow us to relate the population and the distribution of sample means. Think about the trout example we talked about in 8.1. By the way, if you haven't watched 8.1 yet, you got to pause the video, go back and look at 8.1. 8.2 is not going to make sense if you haven't had 8.1 yet. Okay? So the example we used predominantly through 8.1 was about rainbow trout. And we said in this big pond, there's a whole population of rainbow trout with a mean mu and standard deviation sigma. And then we had 100 kids go fish the pond, and they each caught a sample size of 5. Then we took the average of all those samples. So what we ended up with is 100 sample means. And we made a distribution of those sample means. We made a little frequency table out of it. We made a relative frequency histogram. We had a red line estimating the normal curve. Again, you can go back and look at page 318 to see that. And we went from there. Point is, we have a population of all these rainbow trout, and then we have 100 samples that we calculated the mean for, so we have 100 sample means. What 8.2 is all about is relating the distribution of all the fish in the pond, the population, to the distribution of the sample means. Okay, so those are kind of the two worlds we're operating in, population and all the sample means, and we're going to relate the two. So here's what theorem 1 says. If I have a population that has mean, mu, and standard deviation sigma, and it is known to be normally distributed, then the following facts are true about a random sample of that population with mean x bar and standard deviation s. We're setting the scene here. The premise of theorem 1 is that the population is normal. That whole population is normal, and now we're going to, because we know that population is normal, make some decisions and some assumptions and learn some consequences about the distribution of sample means. The distribution of all the trout in the pond is normal, which in turn is going to allow us to learn some things about the distribution of those 100 sample means. So what are those consequences? Again, go ahead and write down the consequences. I'll fill in the blanks here, and then listen to my explanation of it. So the distribution of the sample mean can be assumed to be normally distributed. The mean of the distribution of the sample mean, mu of x bar, equals the population mean. And the standard deviation of the distribution of the sample mean is sigma of x bar. Okay, so go ahead and write this down. Pause it, write it down. Then come back, and we'll go ahead and talk about it. Okay, so again, population is normal. What's that mean for the distribution of sample means? Remember, we've got our whole population, all the rainbow trout. Then we take the 100 sample means we have, and we make a distribution out of those, and we're relating the two distributions. So number 1, if the population is normal, the distribution of sample means can be normal. You could imagine it a little picture. We have all the fish in the pond having a normal distribution. Means those 100 sample means also have a normal distribution. That's consequence number 1. Consequence number 2, the mean of the population is equal to the mean of the distribution of sample means. The means will be the same. Again, we talked in 8.1 about using statistics to make predictions for parameters. If I know the population's normally distributed, then I know that the mean of the population is the same as the mean of the distribution of sample means. So I could use the mean of the sample means to make the prediction as to what the mean of the population would be. Again, this is all based on the fact that the population is normally distributed. So mu of x bar, the mean of the sample means, mu of x bar, will equal the population mean, mu. Mu of x bar is the mean of the sample means. Our third consequence, the standard deviation of the distribution of sample means is sigma of x bar equals sigma over the square root of n. What this means is if I have those 100 sample means and I take the standard deviation of those 100 sample means, my standard deviation will equal that of the population standard deviation divided by the square root of n. Okay? Unlike the mean, where the population mean and the standard or the population mean and the mean of the sample means are equal, that's not the case for standard deviation. With standard deviation, the standard deviation for the distribution of the sample means equals the population standard deviation divided by the square root of n. Okay, so those are our 3 consequences. The population is normal. It means that A, the distribution of sample means is normal. B, the mean of the distribution of sample means equals the population mean. And C, the standard deviation of the distribution of sample means equals population standard deviation divided by the square root of n. Okay, so what's that mean going forward? This means that for any sample size, The X bar distribution, the mean distribution of the sample means, is normal if the X distribution, the population, is normal. Okay, when you read these symbols, know that the X distribution refers to the population and the X bar distribution refers to the distribution of sample means. Okay, so let's actually look at an example. Let's go through, given that definition, how would we actually solve a problem? Well, we're going to keep running with that trout example. Okay, remember, we've got a population of trout in that pond in Wisconsin, and we have 100 samples that we took the mean of each. Remember, the sample size was 5. Each kid catches 5 fish, and we take the average length of them. Then what we do is we make a distribution of all those sample means, and now we're going to solve a problem analyzing it. Okay? So let's say the biologist concluded that the X distribution, remember, as we just wrote down, that's talking about the population. The X distribution of all the fish in the pond is normal, with mean, mu equals 10.2, and sigma equals 1.4. Remember, mu and sigma all talk about the population. So what we're saying here is the population is normal with the following mean and standard deviation. So first question, can we use theorem 1? Why or why not? Pause the video, give it a second to think about it. Can we use theorem 1? Well, the answer I hope you come up with is a resounding yes. I hope while you paused the video, you looked back at theorem 1 and you recognized that the whole premise of theorem 1 is if the population's normal, the distribution of sample means is normal. Our prompter here tells us the X distribution of all the fish in the pond is normal. The population's normal is what is underlined in red is telling us. Therefore, since the population's normal, the distribution of sample means will be normal, and we're applying theorem 1. So, let's answer a question. We're going to answer 2 questions here. I'm going to show you how to solve both, and I'm going to teach you how to tell the difference between one and the other. Well, what's the probability a single trout randomly selected from the pond is between 8 and 12 inches? How do we figure this out? Well, I want you to actually think back to your Chapter 7 knowledge. What did we do in Chapter 7? We said for normal distributions, if I'm given a data value, I can use normal CDF to find the area or the probability. We also said if we were given an area and that the distribution was normal, we could find data values using inverse norm. Well, what's happening here? Well, we have a population that's normal, and we're told that with the population being normal, they want us to find a probability given data values. That should scream in your brain, normal CDF. I have a normal population, and I'm trying to find the probability a single trout taken from that population is between 8 and 12 inches. Well, then my lower bound is going to be 8. My upper boundary will be 12. And my population mean is 10.2. And the standard deviation is 1.4. When you plug this in the calculator and solve, go ahead and try that if you haven't yet. You should end up with about 84%. 84%. Okay? Now, despite all the business of the definition, hopefully this part seems pretty simple. You've done this before. But let's look at the second question. What's the probability that the mean length of 5 trout taken at random is between 8 and 12 inches? Well, first things first, let's look at the difference in the question they're asking. Mean length of 5 trout taken at random, a single trout taken at random. You see, what this second one is getting at is it's not we're taking a single trout out of the pond and saying what's the chance it's between 8 and 12 inches. Now we're taking 5 trout out of the pond, finding their mean, and saying what's the chance that that is between 8 and 12 8 and 12 inches. Hopefully you see the difference there. Again, single trout out of the pond versus taking 5 trout out, finding their average length, and saying what's the chance that is between 8 and 12 inches. The parallels happening here is when we take the single trout out, we're looking at the whole population. But when I take 5 trout out and find the average, I'm now looking at the distribution of sample means. Do you see the difference there? Single trout out of the pond is looking at the whole population. Taking the average of 5 is looking at the distribution of sample means. So how is that going to be different? Well, folks, this is where we really get into applying Theorem 1, because all the consequences are going to allow us to solve this problem. I can't solve this problem and set it up like I did red if I don't know if the distribution of sample means is normal. We learned that in Chapter 7. You can't use NCDF if you don't know the distribution you're looking at is normal. Well, the distribution of sample means, is it normal? Well, according to Theorem 1, consequence number 1, the distribution of the sample mean can assume to be normally distributed if the population is normal. Which means for us, okay, I'm looking at the distribution of sample means. Can I use normal CDF? Yes, I can. Okay, because the population is normal, the distribution of sample means is normal. Well, my left boundary is 8, my right boundary is 12. Now, I don't need the population mean. I need the mean of the sample means and the standard deviation of the sample means. This is because I'm looking at the distribution of sample means, not the population mean. Well, let's look back at our theorem. According to our theorem, if the population is normal, the mean of the distribution of sample means equals the population mean. So, what is mu of x bar? Well, since the population's normal, the mean of the distribution of sample means will match the population mean, so it's 10.2. What's our third consequence? What's the standard deviation of the distribution of sample means? Well, to find that, I take my population standard deviation divided by the square root of n. I take my population standard deviation and divide it by the square root of my sample size. With the trout example, there were 5 fish per sample. We took 100 samples, each had 5 fish. When we set this up and solve, you should get something around 99%. It's 99.76% to be exact. And what I hope you see, and really the bigger picture here, is not just how do I solve each problem, but the difference in the two. The difference in the two problems. You see, here we're working with a Chapter 7 problem with what's in red. I'm just pulling a single trout out of the pond. What's the probability? We have advanced beyond that. We don't just want to know that. We want to know the probability of taking 5 trout out of the pond and taking their average and finding the probability that that average is between 8 and 12 inches. You have to recognize the difference in how the questions are asked. If we are talking about taking the average, the mean length of the trout, we're talking about all those sample means. We got to use that distribution. If we're just taking a single trout out, we're looking at the population. Okay, and so we use the population mean and the population standard deviation. You gotta recognize which distribution you're working with dependent on the question they're asking. Okay, and we'll get more practice with this as we keep going. But this is how we're gonna set up and solve our problems. Theorem 1 says if the population's normal, the distribution of sample means is normal, which allows us to use tools like normal CDF. But we need to interpret, since we have two normal distributions going on here, the population and the distribution of sample means, which one they're asking us questions about. And that will come from the phrasing of the question. Okay. So looking, the final point for this first part is to analyze why were our answers different? Why, when I took a single trout out of the pond, did I end up with an 84% probability? But when I took the average of 5 trout, I ended up with over a 99% probability. Why are those different? Well, if you look back at the problem we solved, the only difference you'll see, the left bound didn't change, the right bound didn't change, the mean didn't change. What changed? What changed was the standard deviation. You see here we used the typical population standard deviation because we were looking at the population. But here we use the standard deviation of the sample means, which is equal to the population standard deviation divided by the square root of n. How does that affect our answer? Well, look at the physical numbers. 1.4 versus 1.4 divided by the square root of 5. This guy is smaller. Your standard deviation for your distribution of sample means was smaller because you divided by the square root of 5. If you'll turn in your books to page 323, you can see how this affects it. Look at the graph at the bottom of the page at 323. On the left, we see the graph of the probability a single trout is drawn. On the right, we see the probability that the average of 5 trout is between 8 and 12 inches. And you can see that there is more area in the blue shaded region for what's on the right, the average, versus just pulling from the population, the graph on the left. And why should that make sense? Because the standard deviation for the distribution of sample means is smaller. And we talked about this in chapter 3. The smaller the standard deviation is, the narrower that curve gets. It goes from a typical curve to a really skinny curve. And you can see that in the picture. The curve on the right that represents the average of 5 fish is skinnier. The smaller the standard deviation, the skinnier the curve. When that curve gets skinnier, more data gets packed between 8 to 12. So the percent ends up being higher. What's the point? Your probability values, when you're working with the distribution of sample means, will always probably be a little bit higher than when you just work with the straight up population, because the standard deviation of the distribution of sample means is smaller. Smaller standard deviation, skinnier curve, more area between the data values we're interested in. I'll say that again. Smaller standard deviation makes our curve skinnier, means more data present between our two values, which ultimately gives us higher probabilities. Smaller standard deviation, more area, higher probabilities. Okay? So that concludes part 1 of our 8.2 video. Specifically, we have covered one of our two big theorems. We covered theorem 1. What is that summarized? If your population distribution is normal, remember we're looking at 2 distributions, population distribution, distribution of sample means. All the fish in the pond, the 100 sample means. If your population is normal, then those 100 sample means will also have a normal distribution. The means of both will be the same. The standard deviation of the population will be sigma. The distribution of the sample means will be sigma divided by the square root of n. Hopefully that's kind of making sense. If it's not, star the parts that are confusing and let me know via email. Okay, that's part 1. Part 2 coming shortly. Thanks, guys.